This is a third of the videos that I've done now on exothermic and endothermic reactions. And in this video, we're going to look at calculating the net energy transfer in a reaction. So we're going to do some bond energy calculations. Now, every chemical reaction either takes in energy, is endothermic, or gives out energy, is exothermic. And if we know how much energy it takes to make or break a bond, all the bonds, then we can calculate how much energy it gives out, or how much energy the reaction takes in. And that's what we're going to do here. So I've got the classic example here of methane, CH4. Methane is gas that comes out of the gas tap, reacting with oxygen, and it makes carbon dioxide and water. There's our equation for it there. And I've just kind of broken it down here. Now, in every chemical reaction, the first thing that happens in every chemical reaction, the first thing that happens is bond breaking. So all the bonds of the reactants are broken. So I've got these carbon-hydrogen bonds here, and they are broken to make carbon-hydrogen all on their own. We have kind of this intermediate stage that exists for a nanosecond before new bonds are made. So the first stage, bond breaking. All the bonds are broken. That requires energy to be put in. Okay. Next stage that happened after all the bonds are broken is new bonds are made. So this carbon is going to join to a couple of oxygens to make carbon dioxide. The hydrogen, a couple of hydrogens are going to join to an oxygen to make water. And bond making gives out energy to the surroundings. So there's a couple of things you have to know, and this was all in video 2, so if this makes not a lot of sense to you, go back and watch the first couple of videos. But bond breaking requires energy to be put in, and bond making gives out energy. Okay, so if we know that, and if we're comfortable with that, we can get into the calculation. So what I want to know here is how much energy is given out to the surroundings. I know this is exothermic, methane burning, a gas tap burning. We know it's exothermic, so how much energy is given out to the surroundings when that happens. So the first thing we have to do is we have to identify what bonds are in the reactants. So we've got carbon-hydrogen bonds, and we've got 4 of them. So you can see that there. We've got 4 carbon-hydrogen bonds. Carbon-hydrogen number 4. Now, once we know that, we need to come to a bond energy table. So I've got a small bond energy table here. Now, these numbers are always given to you. You do not need to learn them. So let's write that. Do not learn. Okay. Constants like this are given to you. Data like this is given to you in an exam. A carbon-hydrogen bond has energy of 413 kilojoules per mole. So in other words, 413 kilojoules of energy is given out for every mole of carbon-hydrogen bonds that are burnt. 413. Now we don't have one of them, we have 4 of them, so we need to multiply that by 4. 4 times 413, 1652, if my mental maths is correct. I should quickly check that before I embarrass myself and putting the wrong answers down. So 4 times 413 equals 1652. Good. Right. Next bond, we've got these oxygen-oxygen double bonds. This is a double bond, okay? It's not 4 single bonds, so that's a classic mistake. This is 2 double bonds. There's 1 double bond there, and there's our second double bond there. So we've got oxygen-oxygen double bonds, and we've got 2 of them. Up here, oxygen-oxygen double bond, 498 kilojoules per mole. 498 kilojoules per mole. So 2 times 498, that's going to be 996. I'm not even going to do that in a calculator. That's my mental maths. I'm quite comfortable with that. So the total energy needed to break all the bonds is now these 2 added together. 2 and 6 is 8. 5 and 9 is 14. 10 is 16. And 2. 2,648. I will just do that on the calculator again just to double check it. So that was 1652. Plus 996 equals 2648, 2648. So it's 2648 kilojoules per mole to break all the bonds. Okay, so first stage of any reaction, bond breaking. Next stage of reaction, bond making. Okay, so we've got carbon-oxygen bond there, and we've got 2 of them. Carbon-oxygen bond, 805. 2 of those, 1610. And we've got hydrogen-oxygen bonds. How many of those? 1, 2, 3, 4. The real secret of doing these questions is accurately counting the number of bonds you've got. 464. 464. 2,624, I'm guessing. Let's have a quick look at that. What do we say? 464 times 4 equals 1856. 1856, oh, that sounds better. 1856, so 0 and 6, 6, that's another 6, 14, 1 to carry, so 3,466 kilojoules per mole. So we've calculated the energy that is made when new bonds are made by first off counting the number of bonds that are made, working out how much energy it takes to make one of them, and then multiplying that out, then adding them together. Okay, so 2648 to break bonds, 3466 to make bonds. So to work out the overall energy change in the reaction, we have to do bond breaking minus bond making. So we're going to take that number there to here, 2648, minus that number there, 3466, 3466. Let's put that in so we can see it. And we've got 2648 minus 3466 minus 818, okay, equals minus 818 kilojoules per mole. Okay, minus means exothermic. Okay, positive, if it were positive, it's not in this case, but positive equals endothermic. Make a note of that. Okay, so this is exothermic, 818 kilojoules per mole. What follows now in the book is lots of examples of that, lots of questions for you to have a go at. So we'll have a go at the first one here, and maybe if we have time, another one, but we'll see. Right, so we've got first stage in any reaction is breaking bonds. So here we've got ethene reacting with steam to make ethanol. So ethene has a carbon-carbon double bond, so it's got 1 times carbon-carbon double bond. Okay, so we have to look at our bond energies up here to find our carbon-carbon double bond. There it is there, 614. Note, that's a single bond, 348, but this isn't a single bond. It's a double bond, 614. Not twice as strong, just about 1.5 times, I suppose. So that's 1 times 614 equals 614 kilojoules per mole. Now we've got 4 times carbon-hydrogen bonds. Okay, so that's 4 times carbon-hydrogen. 4 times carbon-hydrogen, so that's 4 times 413 equals 1,652 kilojoules per mole. 413 was the carbon-hydrogen bond there. But don't forget these. So we've got the water. We've got bonds in the water. We've got 2 oxygen-hydrogen bonds. There's one, and there's the other. So we've got 2 times oxygen-hydrogen. 2 times 464. 2 times 464. Let's do that one on a calculator. 2 times 464, 928 equals 928. Now to get bonds broken total energy, we need to add all these up. 928 plus 1652 plus 614. 3,194 kilojoules per mole. That's bond breaking. Now we need to do bond making. Okay, now this is where people start to go wrong because they miscount bonds. Okay, so they'll forget a carbon-carbon bond or something, or maybe a carbon-oxygen bond. They're the standard ones to forget. Let's do those two first. 1 times carbon-oxygen. So that's 1 times carbon-oxygen. There it is there. 358. 358. 1 times 358 is 358. Let's do this one now. Carbon-oxygen. We've done the carbon-oxygen. Let's do the carbon-carbon bond. 1 times carbon-carbon. The carbon-carbon single bond. Where's that gone? There it is there. 348. 1 times carbon-carbon is 1 times 348 equals 348. Right, now we need to do the oxygen-hydrogen. 1 times oxygen-hydrogen. We did that one over here a moment ago. That's 464, wasn't it? So that's 1 times 464 equals 464. And finally, 1, 2, 3, 4, 5. 5 times carbon-hydrogen. 5 times carbon-hydrogen. Carbon-hydrogen, 413. 5 times 400, 2,000, and 5 13s, 50, 65, 2,065. I'll check that on a calculator. 5 times 413. So 5 times 413 was 2065. Right, good. So now we've got all those in, we just need to add all these up and check we've got all these right. So 265 plus 464 plus 464 plus 348 plus 358. 3,235. So adding those up, 3,235. Run out of space a little bit there, haven't I? Never mind. Let's just rewrite that over here. 3,235. Okay, so if this is an exam situation, I have made that utterly illegible, so I do need to make that really clear. Okay, that is the bond made energy. Okay, so we've got the bond breaking energy and we've got the bond making energy. All right, so what we now need to do is net energy transfer. The overall energy transfer is bond breaking minus bond making. This is the last thing we need to do, making. All right, bond breaking, 3194 minus 3235. So 3194 minus 3235 equals minus 41. So this reaction is just slightly kilojoules per mole, of course. This reaction is exothermic. So that equals minus 41 exothermic. Okay, and minus is important. Minus 41, minus 41. Right, it's quite a long example. I probably could have set it out a little bit better. I think I might just have time. Let's just have time to do this last number, this example number 4 down here. Okay, bonds breaking this time. So it's 2 times hydrogen bromide. 2 times hydrogen bromide. Okay, hydrogen bromide down here, 366. 2 times 366. 2 times 366, 732. 732 kilojoules per mole. So that's the breaking. Making now, I've got a hydrogen, 1 times hydrogen. Hydrogen, where's that? There, 436 equals 436. And I've got 1 bromine, 193. 1 times bromine, 193. Add those two together. 436 plus 193 equals 629. Okay, so breaking minus making. So this is the breaking. We always break bonds to start with. 732. 732 is breaking minus making. There's our making, 629. Minus making, 629. So let's quickly stick that in the calculator. 732 minus 629 equals 103. Now that is positive, so that is endothermic. Okay, endothermic. That's an endothermic reaction. More energy is needed to break bonds than make bonds. And that is bond energy calculations.